Montreal. I have to get my little bit of French in, right, as a Canadian. So it's my pleasure to introduce Dr. Jeff Joyce, who's giving our keynote today. Jeff comes to us from Critical Systems Labs, Inc., which is a Vancouver-based company, but it operates worldwide, consulting on the specification, analysis, and certification of software-intensive critical systems. Jeff has more than 30 years of experience working on the design and application of formal methods, starting from his PhD with Mike Gordon way back at the University of Cambridge at the beginning of the Hall theorem proving system, which I know some of you are familiar with. Jeff has helped to develop some of the important standards that many of us are familiar with, like DO-178C, which is the airborne one, and ISO 26262, which is the automotive standard. So I'm looking forward to Jeff sharing some of his wisdom with us today, and without further ado, I'm going to turn it over to him.
Good morning, and thank you very much, Nancy, and thank you indeed to the organizers for having me here. It's a real privilege. I feel like a bit of an imposter. I'm not a formal methods researcher, but I once was, but I'm not anymore. I'm instead a person who tries to get industry to use formal methods, and so I hope I have something to share with you. Well, yesterday morning when I arrived at my hotel, I noticed I'm staying across the street at another hotel, and you know, on the menu of activities there was going on in the hotel, there was a workshop titled "Why the World Needs More Lawyers." And well, I run a business, which means I deal a lot with agreements, employment agreements, IEP contracts, and so forth. I see too many lawyers, so I had a lot of negative thoughts about that. And so it truly is a great pleasure to come to a workshop in which it might as well have been titled "Why the World Needs More Formal Methods Experts." So that's a much more encouraging type of workshop to be involved with, so thank you for organizing this, not just this year, but a very successful period of history that it's been running. And I'm sure I'll be back. So I came up with this curious title, not because I want to say I doubt this is useful and you should all go home, and because there's no point. Really, I'm saying that in order to use formal methods effectively in, say, practical applications, getting industry to use it, in particular to use it for certification, that one needs to start with doubts about why this is a good idea. And it's through that process of having doubts that can emerge a better understanding of how it can be used properly in order to satisfy the needs of industry, say, when it's being used to certify safety critical products. So that's the story behind the title. And I know the organizers of this workshop are keen on looking for ways to bring the powerful ideas that we already heard about this morning and put these into practice where they can be used by industry. So I'm doing my bit to try help with that goal. Oh, we could skip all that. So I was practicing, you know, I was on Google trying to figure out how to say this guy's name. Stanislav
Leszczyński.
Christoph. I mean, who better could be sitting in the front row to help me with his name? So he was, did you know this? He was the longest lived Polish king. He was a figure of the Enlightenment in Europe. And I mean, he was a patron of science, and he was actually quite an efficient, apparently capable ruler, administrator. So we don't see too many of these days. But so we have a lot to admire in Stanislav, and I think these words are exactly what's in my mind as I start this presentation. To really be certain about how to use formal methods for the purposes of certifying something, say, safety critical or security critical, that one must begin with doubting that it's a good idea. And from that, we can understand what's needed. So just very briefly, where do I come from? Nancy mentioned that I work for, and in fact I'm the head of a company in Vancouver, an engineering consultancy, and we work across a variety of different industry domains, and these are just some of them. And we've been around for more than 15 years now, which is, I think, shows that we've achieved something. And it's interesting, most of our clients are repeat clients, so that is some sort of confirmation that we've done something useful for them. What do? It's really the nexus, or it's these three spheres that we operate in: safety engineering, cybersecurity, and system engineering. I would say sort of cybersecurity less, though we have projects going on today in those. And it's what we really like is the nexus of these three, where these three different disciplines intersect. We have a very interesting list of clients, and these are some of the more recognizable clients. I won't go through all the list. Some of the more exotic ones, let's say, are ITER in France. It's a nuclear fusion, so that's not fission, that's fusion. Experiment, it's really more than experiment, they're building a big reactor. And we were involved in some of the very early work on the protection systems, which you could think of as safety systems. CERN, we've had 5 different projects in CERN in Geneva, the particle physics accelerator there. Those are some of the more exotic ones. And we've done some very sort of, I won't describe them as mundane, but sort of more ordinary things, like worked on big hydroelectric power dams, some of the control systems there. So it's a very nice mix of things. And the interesting thing for us is that the reasons, the methods that we use to, say, build confidence in these systems, including verification and sometimes including formal verification, we see the same sort of patterns over and over in these different industries. I'll just collage of pictures of some of the strange things that we've worked on. We do submarine navigation systems. It's very hard to navigate a submarine. There are no windows, no signposts, and you can't have your sonar on if you're sneaking up on somebody. So that's very interesting, that kind of work. I always get asked what this is. This is in fact one of our very early projects. It was a device that used lasers to treat brain tumors. And so it's inserting a little thin tube into the middle of a tumor and firing it. You can imagine there's some confidence you would like in that working correctly. So we have seen, at the coffee break, if anyone wants, I'll tell you a funny story about that. But what I thought was on the tray covered over by a piece of linen, I thought it was danishes or pastries for coffee, but it in fact wasn't. I'll tell you that story another time. So 30 years ago, I had less gray hair, probably weighed quite a bit less. And I was a graduate student, and in fact, 30 years ago today, I was probably pounding away with the Hall theorem prover, trying to prove a theorem about a little microprocessor and a compiler for that microprocessor. I was trying to show that if you compiled this program using this compiler and you ran it on this hardware, that this would be exactly the behavior of that combination of a compiler and hardware. Today it would be an afternoon's exercise given the advancement in formal methods, technology, let's say. But there it was hard work, it was worth a PhD. And that's a photograph of part of the little, I actually designed this little chip and somebody fabricated it for me, and so I felt very happy at the time. It was the first formally verified silicon in the world, I think is what it was described as. And after my PhD was finished and I was up on the wall framed, I realized there were actually 2 mistakes in the formal proof that I did. And they counteracted each other. This one kind of reversed the badness of this one. So the proof went through even though the compiler was wrong and the hardware was wrong. And I think that's bothered me for 30 years. I had proved something was correct, in fact, and it wasn't correct. I got my degree, but it was wrong. So what should have I done to really remove that doubt? What can I do to remove this doubt? I'm still worried about it after 30 years. So. But it was a good lesson. Don't be overconfident in when you prove something. You should think about why it's really true. And very sincerely, that is a motivation for me as I speak to you today, is I want to think about what really makes this true. So since then, and much more recently, my colleagues and I have been involved in a couple of formal methods projects. We can't talk about them all, but we can talk about a few of them. One of them was this one at CERN. I mentioned CERN earlier, so probably most of you know about CERN, big tunnel, all the dangerous parts under France, all the safe parts under Switzerland that crosses the border. And there are some really dangerous things going on down there. And we were asked to do a safety review of about 5 different projects. One of them was a safety review of the main way in which they detect that things are going badly. And there was a very curious piece of hardware in that I realized only one person, a young PhD student, actually understood how this chip worked. And that wasn't good to me, that only one person understood. So I spent a whole plane ride back from Geneva to Vancouver trying to do on paper a proof of why this was actually true. And just as the wheels touched down in Vancouver, I completed the proof, but it was done literally on napkins. I didn't have any paper. I literally went in from the flight attendants, got napkins, so I had these scrunched up napkins with the proof. It wasn't too convincing in that form. So I managed to get together some money and people to do a formal proof using the Hall theorem prover, and we proved a theorem that is summarized there. And that was very nice work. It was very nice because we could talk about it publicly, since CERN keeps nothing private. More recently, we did a project for Pratt & Whitney, who make engines. If you've flown on an Airbus Neo, that's the engine that's on that aircraft. And I can't talk about what we did there, but afterwards the authors, or the engineers that I was working with, one of whom is the person who certifies the software on that airplane engine, were so intrigued, and I think it's fair to say impressed by what we had done for them inside a project, that we did a little research paper that kind of illustrated the sort of essence or gave an idea of what we had done without revealing what actually we had been done. And so this might look like a very simple circuit. The truth is that it was a very complicated circuit with lots of other things going on in it, and we extracted out of this Simulink model something of interest, and it turned out to be a very interesting result that we obtained by using model checking in that case. So, although I'm not a formal methods researcher, I'm keeping my hand in formal methods, and I have the privilege of having some very strong colleagues, 2 of whom are here in the room, who are really the brains now behind how we use formal methods, and I just get to watch them do interesting things. So, certification is the process by which we determine that we prove in some sense or certify some system or a software system or a combination of hardware and software for use. And different industries do this in different ways, and they use different words for this, but just for simplicity I'll call it certification. It's a hugely costly part of developing a safety critical system. Some people say it's 2/3 of the cost is the certification process. And so any proposition you can make that you could lower the cost of certification by using formal methods, say to reduce the amount of testing, or to reduce the amount of redesign of a system, or to find problems before you've implemented the code, because you can apply formal methods to an algorithm or a design rather than waiting for the code to be implemented, that's going to catch someone's attention. But if they actually want to use the results of formal verification for certification purposes, that is in some sense an even bigger challenge. Because the way that the world of certification works, they're not used to formal methods for the most part. And just saying, oh, well, you know, forget about this testing, here's my theorem prover or my model checker, and it's produced the result true, that's as good as 4,000 pages of test results. That's not going to be an easy thing to convince an assessor of. So this is really an important question. You'll often get asked this question, well, what's the return on value in using formal methods? And you can come up with a good answer to that often. But the next question they'll ask you, once they get more interested, is, well, how can I be sure that these results will be a substitute or a partial substitute for what we would otherwise have to do? Because they really don't want to decide to use formal methods at some cost and then realize that they still have to do what they would have done anyway, which is with conventional testing. There's no cost savings there. You might be thinking, well, but it's better, it's better. That doesn't really work too well on the financial side of things. They want not just more and better, but they want cheaper. So you have to think about, how can I really give up some testing and use formal methods in its place? So certification is usually driven by a standard or some guidance, some published document, usually put together by industry experts. And that kind of serves as, sometimes it's the authoritative specification or the authoritative standard. You have to do this. Sometimes it's an optional to use that, or in theory it's optional to use that standard, but in practice to do anything other than comply with the standard would be an unwise move. So here are 3 examples. This is RTCA DO-178C. This is Aerospace. All aerospace software is certified against this, or most is certified against this. This is the automotive standard, ISO 26262, and this is one for rail. I was a member of the committee that wrote the most recent version of this one, the aerospace standard, and I was a member of the committee that wrote this one, the automotive standard, ISO 26262. So I've had the good fortune to see how these standards are put together and what the rationale is for whatever goes into those standards, and often what the sort of hidden meaning behind the sentences are in those standards. In my day-to-day work with my colleagues, we often are in situations where we are helping clients comply with these standards, and that interaction with our clients, that support of our clients starts early in the process. But as things proceed, eventually we get to the point where now they've finished the work and they have their certification package, their set of evidence that they put in front of a certification authority and say, see, we've complied with the standard, and then it's a long process of picking over the certification authority. The assessor goes and picks over what's been presented and tries to find holes in it, tries to find something wrong in it. And I spent a lot of time replying to these objections and saying why this is good enough. Or sometimes we admit, no, there is something missing, and then we go and we fix it. Now these standards are typically very test-oriented. That is the method of verification. At least in terms of verifying the executable code, there is also some sense of verifying the requirements, which means checking the requirements are complete and consistent. There's also verifying the architecture, verifying the design, verifying the source code, all of which is not testing, that's usually review and inspection. And then there's testing, which is verifying the executable code. But they're all, at least with respect to verifying the executable code, they're very test-oriented. And here, for example, from DO-178B, so the previous version, this slide just happens to come from the earlier version the aerospace standard. This is the famous Table 7. It has a curious name, verification of the verification results. It isn't a cut and paste error, it's intentional. What it means is somebody has verified the use test to verify the code. But then somebody has to check that that verification result is correct and complete, that we've done enough testing. So that's what it means by verification of the verification. We're verifying the verification. So this is one of maybe two, I think it's a dozen tables in the back of DO-178B and C2. C, I think, is the same as this one. But look, every one of these has the word test in them. The test procedures are correct. The test results are correct. We've achieved a certain amount of test coverage. It's all about test. That's hardwired, hard-baked into the standard. And so if you were to come along and say, well, I've used formal methods to prove that my software in this airplane is correct, the certification authority, it's called, in the case of aerospace, it's called a designated engineering representative, a DER. He or she will say, show me test. Nice that you've done formal methods, interesting, curious, but I want to see the test. And that's the problem with that standard. And the same problem with most of these other standards. So back nearly 20 years ago, Airbus was experimenting with the use of formal methods. They gathered together a bunch of very bright people. I have got to know them, and not unlike some of the young people I see in the room here, very keen about using formal methods to somehow make verification not only better, but cheaper for this new aircraft that was being developed by Airbus. Now, the Airbus 380 hasn't fared that well, but that's another story. But the methods they came up with were very impressive, and indeed they claim, and I have no reason to doubt them, this is in private, they told me, yes, we reduced the cost of verification of particularly unit testing through the use of formal methods, and it was a big win for Airbus. But then Airbus needed to get this airplane certified, and they went to their certification authority with a copy of RTCA DO-178B at that time, the previous version. And I'm simplifying the story a lot, but let's just say the DER, the certification authority, said, sorry, I want to see test. I see nothing in this standard. The standard says you can use formal methods, but it doesn't say you can take credit for it. You just go ahead, use formal methods. Use as a psychologist. Use whatever you like, but you have to do tests still. And so Airbus was left with this problem of how do we get credit for this better way of verifying the system? And Airbus and other people then persuaded the committee that was about to rewrite this standard, this DO-178C, that they should have a dedicated subcommittee which was to answer the question, how can we use formal methods and get credit for it? How can it replace some testing? So all this committee began its work in 2005, so what is that, nearly 15 years ago. And I was at the inaugural meeting of that, and I went through a series of meetings held over a period of about 5 years to come up with an answer, how can we use formal methods and get credit for it in the certification of an airplane. And the final product of that was a document called the Formal Methods Supplement to DO-178C. It's a publication, it has a number of DO-333, and it basically says, how can you use formal methods and get credit for it? It was very carefully written in the sense in two particular ways. It was not a kind of cheering section for formal methods. It wasn't meant to say, yeah, use formal methods, it's great. It does not advocate the use of formal methods. That's not its purpose. It merely explains how it can be applied, and it also tried very carefully not to recommend or endorse any particular kind of formal method. It wanted to be very neutral in terms of, because we know this document will be around for 20 years or so, could be around as long as 20 years, and there'll be advances in formal methods that we weren't aware of when we wrote this, this supplement. And we didn't want to exclude advances in formal methods, so we were very careful to write it in a neutral way, but hopefully not a way that had no substance. Another very important thing about this, and if you were to ever look at this, which I would encourage you to do if you aspire to use formal methods in an industrial application, even if it's not aerospace, because what it says would apply to other domains too. It's written, the audience, the primary audience of this document is not people like you. It's people who certify aircraft. So it was meant to tell the person, the DER, the designated engineering representative, the guy who decides, it's meant to put in his language what he should expect to see, or what would be a reasonable thing to expect to see. Because that's what the DERs wanted, and that was the purpose of the document. So when you look at it, it may seem a little strange at times, and in fact, the way this was written is we literally took a Word document copy of this original, the original main body document, and we went through it line by line, editing it to apply to formal methods. So that you can look up a section in the main body, the main document, and then you can flip to the supplement and see exactly in the same section what the corresponding text is for formal methods. So one of the I think it was actually our second meeting, I drew the original version of this diagram, and now it appears in the standard. It was sort of done over during a coffee break, and we're trying to really identify all the places where formal methods could potentially be used in the, to verify the software that's used in an airplane. And everywhere where you see a solid black arrow or a dashed red arrow is a potential place to use formal methods. And I think that's what struck us at the time, was that there were many different ways and levels in which formal methods could be used. And what the standard says is that you don't have to use formal methods for everything. You can pick out where you would like to use it. So the way to read this, I know it's a confusing diagram, but basically the way the aerospace world looks at software in the context of an aircraft is there are system level requirements. From those, there are high-level software requirements, and below those are low-level software requirements, and then there's source code. So, for instance, a system requirement might say there will be a function that intervenes when the aircraft is stalling to point the nose of the aircraft down. And then there'll be a high level, and it may talk a little bit about the use of a network and so forth. Then there'll be high level requirements that very specifically say what are the conditions under which this safety function would operate. And then these might be kind of unit level or module level requirements. And then source code, of course, we know what that is. So just let's take a look at a few places in that diagram. One potential use of formal methods is to prove what's called compliance and traceability. That's a standard term in DO-178C. You need to show compliance and traceability. And there's a lot of meaning packed into those two words, by the way. There's probably that much text that defines what that means. And you could use formal methods to prove that the traceability and compliance exists between the high-level software requirements and the system requirements. And even if that's all you did with formal methods in the certification of some part of the software of an airplane, that would be recognized by the standard as a good or as a legitimate use of formal methods. Another possibility is to prove a relationship, their compliance and traceability between the low-level requirements and the high-level requirements, or even between the source code and the low-level requirements. And I've seen work which is actually between the executable, the binary, and the source code of the binary and the low-level requirements. So there are lots of places where you can apply it, and you can apply it selectively. So the standard is very good, this supplement, I should say, at saying here Mr. or Ms. Certification Authority are legitimate places where formal methods can be used in such a way that they are a legitimate substitute for results that would be otherwise obtained by means of testing or review or inspection. Where the standard is a bit thin is how do we really know that what's been done is a formal method? Or is that this is not just some heuristic or some thing that somebody made and nobody can understand, but everybody believes it's a legitimate formal method. How do we really know that it's real? About all the standard says is this. I'm sure if we dug through the text, might find a bit more, but I don't really think so. And I went back yesterday and convinced myself of this. It says, well, you have to be using a notation, which could be a graphical notation, not just textual, which is unambiguous, has a mathematically defined semantics and syntax. We have to have some way of showing its sound. I remember I was the one on the committee saying soundness, it has to be sound, and there was a lot of pushback about that. You know, what would that mean? How would a DER know it was sound? Because everything, you know, everything we talked about at that committee was how would this design engineering representative or designated engineering representative understand what he or she was looking for. And then there's some assumptions underlying the formal representation of the model that need to be justified. So the presentation just before the coffee break I was most interested in, thank you, excellent presentation, because you were saying you have a way of taking a more complex timed automata and turning that into a less complex one. Is that fair enough? So I wanted to ask you the question, how do you know that transformation is correct? And you probably would have a very good answer for that. Pardon? We proved it. She has proofs. So, I mean, the assumptions have to be justified, and she has a proof. How do you know your proof is good? Well, we'll talk more about that. You can see how annoying I would be if I was a certification authority and you were presenting your work. Well, how do you know that? I mean, so let's play a little game. Okay. Let's just suppose that by chance you are involved with a project concerning some functionality that in an airplane, some new kind of functionality, and what its job is to intervene when the aircraft is stalling. The aircraft is flying at too high of an angle of attack, and the speed is not enough, and so the airplane is beginning to lose lift or is at risk of losing lift. And so what this software does is it uses the elevators on the tail to push the nose down, tip the aircraft down. It sounds like if you're stalling and crashing to earth, it sounds like the last thing you want to do, right, is point the nose down. But that's the way to get out of a stall, is to push the nose down with the aircraft so that you gain some speed, some air going over the wings, and then you can recover. So this is an automatic function that intervenes even if the pilot isn't doing the right thing. It's supposed to kick in and take over and push the nose down. And of course, I bet most of you know what I have in the back of my mind if you've been reading the newspapers recently. But we're not talking about any particular airframe manufacturer or anything. It's just a hypothetical exercise. So suppose that you have used formal proof to prove, or pardon me, I'm getting ahead of myself. Sorry. Suppose that you have used formal methods for this purpose, and now it's been folded into what's called the certification package, a body of evidence that is provided to, oh, I can see they're taking pictures. It's not, there's no B on this airplane. You
No
have...
B, no A.
There's no A, there's no B. You have contributed to the certification package that's been provided to the DER. And in what you've provided in particular is some formal analysis, some results using the formal methods. And I'll assume it's a tool that you've used. And the DER is now raising some concerns or some objection, as rightly he or she should do. And this is blocking the certification of the aircraft. So there's a lot of pressure, there's a lot of money at stake here to get it certified, but the DER, and I know a number of DERs, these are people who just don't give in. I mean, they're not intimidated at all. So if they don't think it's right, and they're confident, they will have their questions answered before anything happens. So what are the typical kinds of objections they might give? And I've made these up, but I mean, they would be very typical of what I would expect to see. So the first one is, well, you have made a formal model of something, of a real-world cyber-physical system, and in doing that, you've introduced some simplifying assumptions. You are now modeling things at a certain level of abstraction that might miss out some details. And so, for instance, the DER in this case has said, well, you're modeling in your formal model the vertical speed, how quickly the aircraft is going up or down, as an integer, a signed integer, such that when it's positive, that means you're climbing. But what about the case when we really don't know what the vertical speed is? You know, there's a third possibility here. It's neither climbing or not climbing, or we don't know. And your simplifying assumption that you've introduced here has eliminated that consideration. So as the DER is flipping through the certification package, he or she comes to the page where the formal methods results are present. And normally this DER is expecting to see several hundred, if not several thousand pages of test results. And instead they just see a nice blank, white sheet of paper printed out in, 24 bold font is property proved, or property is true, or theorem proved, or something like that. And I know, they would just say, what is this? Why should I'm used to seeing hundreds of pages of results that I can go and selectively point at one and dwell on it and ask a lot of questions about it. This is what I've done when I've done this kind of work myself. You sort of hone in on something and then you just pick away at it until you drive everybody in the room crazy. And yet now they just see, I see two words, property proved or property true. That is just not satisfying. And that wouldn't convince me. I've seen people give presentations and come up with property true, and then it turns out there's something wrong with their model. Remember what I told you when I finished my PhD, I got property true, and then 2 months later, I found there was something wrong. I hadn't actually, I proved a correctness result about a compiler. I hadn't actually run the compiler ever. I never compiled a program because I was so confident in formal methods. If I'd compiled anything with it, I would have seen it didn't work. That's overconfidence in formal methods. And then how do I know your tool is correct? You have this magic tool, and I can tell me as the DER, the certification authority, that you look very enthusiastic and confident about your tool, but how do I know it's really going to work? And your answer might be, oh, well, this tool, it's based on a formal theory, and I correctly implemented that theory. First of all, I have some doubts about that. I mean, there might be a nice theory, but there might be a lot of shortcuts, little decision procedures. Oh, you know, I don't really need to do that all. I can just, you know, I can make this little algorithm over here. It'll speed up my verification tool much faster. But even if I believe you that you have faithfully implemented some theory which justifies what you've done, how do I know this theory that is driving, that is the mathematical basis of this analysis, how do I know that this just isn't nonsense? I mean, in other words, how do we know that this is a sound theory, that it preserves truth? Now, I can tell you at this point, you're pushing it to ask a DER to go into, you know, the soundness of some mathematical theory. He or she really, I mean, that's not typically their experience. Now, they could hire experts, like people in this room, to sort of advise them. But there's a limit, they will have a limited patience for a bunch of hand-waving about why some tool is a correct implementation of a theory and why that's a good theory. They're much more comfortable looking at hundreds of pages of test results. So let's suppose in this case that all of the verification results are of the form, well, if the software is implemented in, if the implementation, if the executable code and the source code that was used to generate that executable code is a correct, or complies with or satisfies the low-level requirements, then the desired safety property would be true. But in certain industries, particularly aerospace, they're almost just as interested in the question, and what else does it do? Things have crashed or blown up because even though the correct functionality was, if the desired safety functionality was correctly implemented, it turns out there were other functions executing on the same software, same hardware, that were the problem. And you could have done all the formal proof you like. If you're just proving results that the right thing will happen, it'll never tell you about the other stuff that's going on in the... Now, aerospace and other industries have a very good answer for this. They use something called structural coverage, and they use something called traceability, which is what gives them confidence that they don't have any of this unintended functionality. And it's very easy to see how people use formal methods and just not address that other half of the coin. And so on and so on. So, what are we going to do about this? I have another idea for you. So, sometime in the last 3 or 4 years, I encountered something called, I and my colleagues encountered something called a limit of induction, or we these days call it a limit of argumentation. And there's a very nice technical report published by some researchers at MIT, which I highly recommend. This paper has been the most interesting and influential paper I've read in the last 5 years at least. And it's really changed how our business works, what we do. And this is not just about formal methods. We mostly do safety analysis. We do what's in this paper. Not exactly what's in there, but pretty close for a variety of different clients, and it's extremely powerful. And the core of the idea, and two of the world's experts are sitting in the back room there. They do this all day long, use this method. They're not looking at me. They're refusing to make eye contact now because they don't want me to put them on the spot. But they really are the experts. If you want to know about this, ask them. But what's the key idea is this: if you want to know something, then doubt it and find all the reasons that it could be doubted, and then examine those doubts. And if you can eliminate them, then you're left with the conclusion that you can be confident in what you try to claim. Just like our good friend Stanislav, help me out, Christoph, Stanislav Leszczynski was telling us, 500 years ago. If you want to know something, doubt it, and then examine those doubts. And that's what this paper is about. And I can tell you, I mean, this is not a safety presentation, so I won't go off on a tangent here, but this has really revolutionized how we do our safety work. And so it occurred to me that we could apply this kind of thinking to the problem we have here today, which is how can we be confident in formal methods? How can we anticipate the doubts that a certification authority might have and have good answers and actually not just, you know, clever answers, but good answers in which we've actually anticipated those doubts and we've done whatever extra work needs to be done to be confident about what we're doing. So let's suppose that we make a top-level claim like this, that the results obtained by means of formal methods are acceptable for certification purposes in some particular context, let's say some particular project, and so on. How would we go doing that? So I'll show you how we go about doing that, and I think we have enough time to make this a bit of an interactive exercise. So,
About 20 minutes.
okay, perfect. Okay, and that'll even leave a little time for questions and discussion at the end. So, if you read the paper for the that I mentioned earlier, I mean, they'll show you how they use GSN diagrams and so forth to construct an eliminative argument. And I really don't care about that too much. I mean, the diagrams are nice and in fact very helpful if you have them in front of you. But it's not really about creating the diagrams, it's the kind of thought process. And what I find useful is just to use a spreadsheet. It's also because I'm sort of tool handicapped. I mean, I can only use Excel and Word these days. So, so I have to use Excel. And so what I do is this. What we do is we'll start in cell A1, our top level claim, just like you saw in the previous slide. And then we'll say, well, but what could be wrong with that? How could that, what doubt could I have about this claim? And I hope some of you are already thinking about what some of those doubts will be, because I'm going to turn it over to you shortly. So we might come up with but this, but that, but this, and so on. At some point, I might even elaborate on some of these doubts. I might say, well, I doubt this because of this reason, or that reason, or that reason, and so forth. So I might have a lot of becauses, and then I might get to a however, and this is where I kind of refute that doubt. If I can get to the point where I feel that I've identified all the reasonable doubts and I've sort of fleshed them out with responses. So red is bad, black is good. I was doing this on Friday with someone, and after 30 minutes he put up his hand and said, I'm colorblind. So if anyone's colorblind, in fact there were 2 colorblind people in the room, I found out later. So if anyone's colorblind, I'm sorry. The buts and the becauses are all in red, that means bad, and everything else is in black, which means good, or on the right side of the law. So however's are sort of rebuttals. Now this could go on recursively, right? Because you could say something here and then someone would say, well, I doubt that, and you could have another layer of doubt and rebuttal. And this is what we do. I was going to show you what one of these eliminative arguments looks like when it's really fleshed out, but I got a tool and I blurred out all the details so you wouldn't see what it really was about, but I decided to leave it out anyway. But they can get quite complex and deep, these arguments. But the beauty of it is that you really discover what you need to worry about, and you have good answers. We've had the experience when we've had certification authorities come back and say, well, I think there could be a problem like this, and we just look at our little argument and we find we already doubted that, we already came up with that ourselves, and here's the answer we have for that. So it's great, and I'm just trying to apply that in this situation. So let's try something really risky, and let's do this in real time. Okay. So this is Excel, and I've just replicated what we saw in that previous slide. Here's our top level claim. And now I want to do some doubts. So I'm a really fast typer, see? But possibly the results are incomplete. I mean, I proved something, but it missed something. Another possibility is that it's always a surprise to me. So I proved something, but it's wrong. My proof is wrong. My analysis tool is wrong. This formally derived result is not trustworthy. This is something I spoke about earlier. Remember when I said the certification authority will see on a white sheet of paper in the middle in large font, property true. And he or she would have been expecting to see hundreds of pages of test results. So they'll say, well, the evidence just lacks granularity for me to review it. And I think that's a very legitimate objection. And what's the final one here? The evidence isn't compatible with the trusted criteria. The standard says test, 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 and you haven't done tests. So even though it might be better, it still says test, test, test. And so I can't use your results, sorry. So those are at least 4. Now, just to speed things up, and I really am getting, I mean, I can sit down and relax after this and let you take over. I'm just going to unhide. I did a lot of this work earlier. Is that getting too small, I guess? Can anyone see that? No, not. Okay, I'll try a little bit. Try a little bit bigger. Okay, I think that's the best I can do. Okay. My apologies to anyone who can't see that clearly, which would be me if I was anywhere but in the first row. So what I really would like with your help to try fill out this argument, either with more doubts, although we already have a lot to work on, or with maybe some responses to these doubts saying, but that could be addressed by this. And if we had all day, which we don't, what would be a very nice result of a workshop like this would be to come up with a set of specific guidance for what needs to be done if one is delivering formal methods for the use in certification purposes. That the deliverable result needs to be more than the words property true. It also needs to be this, and it also needs to be that, and this and this and that. To some extent, the aerospace standard I mentioned, DO-333, says that, but not enough. And it takes people with the kinds of expertise and knowledge that's in this room to really come up with a good list like that. We don't have time to do that today, but at least we can get that started. And who knows, maybe one of you will pursue this. So I'm opening the floor now I need some help. What could we do, for instance, I mean, I could have a doubt that the tool, we heard this morning a number of presentations, some of which involve tools. So where are our speakers? One's here, one's there. Why should we trust you had tools, right? And where's our first speaker? There. And there was someone even earlier, let's see. Anyway, why should we trust the tools that you used?
I would answer how have we been trusting the tools that have been used for certification? If we certify a piece of software, how do we trust the compilers?
How do we trust the compiler? Oh, because this compiler is used, 100 times a second across the world. And if there was any problem with it, we would have heard about it. I mean, I don't mean that as a glib answer. I mean, you're exactly right that we should just turn to how conventional tools that are used are certified. And in the case of a tool that's sort of widely used, is open source, has a complete public history, it's often easy to make what we call a product history argument for it. But if it's a tool that has 3 users, you know, and they only made it last week, that's pretty hard to make a product history argument for that. Now the Hall system, and I noticed we have some Hall papers at the end of today, so that's a theorem prover that was invented by my supervisor a long time ago, my PhD supervisor. It was really, I mean, one of the beautiful things about it is there was a little tiny kernel in it that was if there was something wrong, it would be wrong in this little kernel, you know, and the thousands of other lines of implementation didn't matter. If there were mistakes elsewhere, the tool just wouldn't produce the result you wanted, but it would never produce a bad result. Or it was soundness boiled down to a very small chunk of code, and that's what you had to trust. That's what you had to trust. So it was an interesting soundness argument for the tool there. Any other ideas? So we could use conventional product history, we could do some testing, we could have a kind of a clever scheme of isolating the sort of critical part and saying that's in this little safe kernel that we trust. I see a hand in the back there.
The tool produces additional evidence which can be independently checked.
Ah, beautiful. I know Nancy's had that idea, so for something we're working on. But great suggestion. We could have a clever tool that's full of whatever, as we call it in our work, a barrel of monkeys. We don't care how it does whatever it does something, but it leaves a trail behind. And something simple can go and just check that trail is legitimate. That's a great idea. I wish I should all enhance. Do you want to go into
You want me to go type something?
if you can? I mean, if you can keep up with this, but just I mean, we should have the independent check on the verification result. I saw other hands up.
Tool diversity. Use 2 tools that make this similar
Okay.
thing.
Tool diverse redundancy. Good.
Yes,
Good. So Nancy, just what you
Yeah,
can do.
I'm down to-
If you just look this row right here, where the tool, we could,
I'm trying to add a row.
okay,
Who's an Excel user here? Where do I?
Insert rows.
if you just right click and do, insert.
Search.
You should right click and see,
Yeah,
If you go in the top menu.
Insert.
yeah.
There you go.
See, I only know how to use 2 tools, Excel and Word, but I know how to use them, so. Nancy is working on much more powerful tools.
There you go.
Okay.
Is that what you want?
Yeah, independent on a bread trail, let's call it.
Of a what?
A bread trail, or it leaves the smart tool leaves behind a trace of what it did. And then this independently affected. So that's good, I'll remember what that means. Anyone else? See, I'm using you now to develop something. Okay.
You could rate the development of the tool according to its application standard.
Okay, so, sure.
How often is this in practice? Right.
That people use the standard to sort of, what we call qualify a formal methods tool?
Yes.
I haven't seen that.
Okay, I think, so I'm aware only of the scale, code generator, and this kind of stuff.
Okay,
So I'm also, I haven't seen it.
okay. Simon, I think you want to say,
No, I was saying, I was
Okay.
responding to this question.
okay. Mateo, did you have something? Okay. Okay, so let's go back to the soundness. The formalism isn't sound. Okay? What do we do for time here? I think we'll just do this one and then we'll stop there. How do I know that your method is sound? How do I know that it preserves truth? If I have a timed automata that I start with and I trust it, or pardon me, I have a timed automata and I mean, it's been given to me, I have no possibility of changing it, but I can still apply your technique to reduce it and then do some verification on that reduced one. But I have to know that this transformation was sound, truth preserving. How would I, you did a proof, right?
We actually define this relation perfectly. We
Okay.
give you a relation to show that they're equivalent,
Okay.
and we prove that afterwards, but you can see our relation.
But it must be based on some underlying mathematical theory, right? What is that theory?
Be the semantics of time automata.
Yeah, that's
And
right.
how do you know that's right?
That's by definition. Yeah, that's, somebody's defined the semantics of time automata.
And how do you know they were right? I mean,
Because
maybe
you
it's-
can observe up by simulation.
well, I mean, a good answer that might be, here are 25 publications in refereed journals that say this is a valid idea. This is a, this is a legitimate mathematical theory, okay? And that might be a way to, that might be your evidence for the legitimacy of the theory.
I think I've heard of some theories in other domains that they're shown to be wrong after 10 years
Yeah.
of research.
So you can see, I mean, you could end up, in an institution if you did too much doubting. I mean, you could just begin not to believe. We were doing this, and we have some co-ops, some students in our office, and on Friday I was doing this exercise with them. You could just, we were doing something on airplanes, trains, I can't remember. And you could just see them getting increasingly nervous as they were not believing anything anymore. So you have to sort of learn when to cut this off. Okay? But that's the idea. So I think that's all the time I have in this little presentation. What I hope I've achieved is to make you understand, first of all, or help you understand what are the potential barriers to using formal methods in a certification context. And they may seem silly to you, but they are reasonable, because these areas such as aerospace and automotive, I mean, for the most part, they're dominated by people with gray hair like me who rely on their experience about what they trust. And if they see something different that's unfamiliar, they're going to push back on it. And it's not because they're just old and they don't want to change. I mean, they have responsibility, which they need to use judgment, and judgment is based on experience. And so they're going to ask questions, and you need to be able to answer their questions, their doubts. And that's what I've tried to expose you to today. I have a little prayer that it might inspire somebody in the room to take this further. And in fact, I tried to do this about 8 or 9 years ago with a series of little workshops in Cambridge in conjunction with my former PhD supervisor, where we tried to bring together a panel of people who were formal methods experts and industry experts and try to flesh this out into more specific criteria for how we could sort of establish the legitimacy of a formal methods result. And we only got so far before some things happened and it didn't finish. So maybe someone can take over that mission and come up with something like that. It'd be a great contribution. So that's what I hope I've achieved today. And I think at that, I will just turn it over for questions or discussions. Thank you for those who participated in helping. Thanks, Nancy, for, I know we didn't put you to enough work here.
Yeah. Okay, thank you, Jeff. So let's open it up for questions. Go ahead.
So aren't we in trouble no matter what we do? Because it seems that testing is not enough. And when we do formal verification, we end up having this infinite regression of, well, can we trust the compiler, can we trust the chip maker, can we trust so on and so forth. But at least the formal verification is something that typically covers all possibilities, whereas testing does not, in particular, not when you have concurrent systems, right?
Okay, very good question. No, so first of all, in the committee that wrote the aerospace standard, the supplement about how to use formal methods, was unanimous in some testing is always needed. No matter what you do, there will always be some testing. I wish I had run my compiler when I did in my little PhD project and seen that it couldn't compile anything. but I was too arrogant to think that formal methods, you know, would get it
Well,
right.
just because you formally verified it doesn't mean your implementation of whatever you verified is correct.
Oh, but I mean, my formal model, there was a bug in it. I mean, there were two bugs, they cancel on each other. So there's always a place for testing. And then you said, well, there could be an infinite regression of doubt where we never end. This is where gray hair comes in. You know, there'll be some judgment made at some point that you pushed it down far enough that we seem to have hit, you know, enough sensitive spots that now we can begin to be confident. I'm not too worried about that, to tell you the truth. I mean, it looks, when you first start doing this, it looks like you'll go on and on forever and you'll be done in everything forever. But there is a point when, you know, it's sensible to cut it off. I hope that answers enough of your question. Please.
Yeah. Okay, I have like two questions. Once you, in one of your slides, you said that you are working with the QNX, and I know that they are providing certification for 26262, and also you are also providing certification. So how can you collaborate with them? Like, you take the software from them and then use it and then give it to the other manufacturers, or like you give the like services to the QNX and then they do.
So basically your question, you've noted in one of our slides that one of our clients, indeed a very important client, is BlackBerry QNX, and indeed we work with them quite a bit. And you know, I can't tell you exactly what we do there, but I mean, I can tell you this much, that we work alongside with them on certification projects where we're really sort of operating hand in hand with them, helping them achieve their goal, which is to get certification. So we're part of their team, let's say, put it that way. We're not checking on what they've done. There are other people who come and check on what people give them literally a certificate, you know, that they frame and put on the wall. And there's other people who come and do that and have no connection with development.
Okay. The second thing is that you talk about, okay, you have doubts, whatever you say, you put a doubt on it. But we also know that no system in the world which is safe. There always be some failures or errors.
Sure.
So, I mean, you have to be put a line that, okay, this is something acceptable, like the concept of alarm. The failures are as low as it can be acceptable. So, like for this case, I think that like for the theorem provers or the formal methods, at least we have a bit of confidence, or maybe we can say it's proven in use, that for many years like people have used these tools and there isn't any like fatal bug in the software.
Like with this theorem prover you're saying?
Yes.
Yeah, so that's a product, what we call a product history argument.
Yes.
You know. Now, that just says the tool's fine, maybe you've misused it. I mean, I've seen people write theorems that they, you know, say essentially this is correct, this implementation, and it's misstated.
Okay, we'll take one more question because I know the time is tight. I'll get you to come up and set up for the next one. So there was a gentleman there who's been waiting now.
Me?
Yeah.
Okay. About the infinite regression of doubting, or the linear good argumentation, and you have to put an end. Could this, I understand that it is not easily measurable, but could we put an end that is dependent also on the development assurance level or safety integrity level as for the testing? Because also the testing, you go in depth to a level, according to this. Do you think this can be viable?
So the question is this: standards include some criteria for the qualification of conventional tools, and those criteria are often linked to the safety of the product itself. If this is a very critical device, then it has to meet this level of qualification. And in this regard, I would view a formal analysis tool as no different than a conventional tool, that it should be just applied to the same criteria, same qualification. But I don't think that's the whole answer. That's part of it. Has this theory been correctly implemented? But it's not going to help you with, is this a correct theory? Okay. So, thank you very much. I should get
Yes.
underway.
Yeah.
I'm sure Jeff would be happy to talk more with everyone at lunchtime and at a later break. So we need to go on and keep on schedule, so